Alright, in today's class we'll be talking about gamma function, mass 204. Now, but before we start, I would like us to understand why we introduce the topic called gamma function. Okay? So gamma function was introduced by a Swiss mathematician, Leonhard Euler, to help us extend the factorial operations. Okay? We all know that factorial is only meant for natural numbers. Are you getting it? So we are not, I believe you don't know that you can obtain a factorial of rational functions, factorial of non-integer functions. I believe you are not aware of that. You know, like if somebody asks you to obtain the factorial of 3 over 2, you find it difficult to do that. So the one you know is only 3, 4, 5, 2, 1, factorial of natural numbers. So today we'll be talking about gamma function. In case you are asked in anywhere, why are you learning gamma function? Just tell the person it is used to enhance, generalize the operations of factorial numbers or factorial functions, factorial operations. Now, today we'll be looking at the definition of gamma function. We said that the integral from 0 to infinity of exponential minus t raised to x minus 1 dt is equals to, is defined as the Now this is the definition of gamma x. We said that integral from 0 to infinity exponential minus t raised to x minus 1 dt is defined as the gamma function of x for every x greater than what? 0. Now, this could be written as, it is also written as gamma x equals to integral 0 to infinity exponential minus t raised to x minus 1 dt. Okay, so look at the definition here. This part is the part that defines the function x. So this is the complete definition of gamma x. Okay, now with this, one can find the factorial of non-integer functions, factorial of negative non-integer functions, unlike before. Okay, so now we will go ahead to look at properties. Properties of gamma function. We are going to look at properties of gamma function. Please, in these properties of gamma function, we all have to be, careful to understand the way I'm going to develop it, because in some exams you will be asked to prove some of those properties, and if you are asked to prove some of those properties, you have to apply any of this approach. Number one property, we are told that gamma 1 is equals to 1. We are told that gamma 1 is equals to 1, and we have to prove it. Gamma 1 equals to 1, we have to prove it. So for us to prove that gamma 1 is equals to 1, we are going to make use of the general definition of gamma x. Solution. know that gamma x is equals to integral from 0 to infinity exponential minus t raised to power x minus 1 dt. We know that gamma s is this, right? In this time around, x is acting as 1, x is 1, so which means that we can define our gamma 1 as equals to integral 0 to infinity exponential minus t raised to power 1 minus 1 dt. Okay, having in mind that x is 1. So from here, we have that gamma 1 is equals to integral from 0 to infinity exponential minus t raised to power 0 dt. Okay, 1 minus 1 is 0. So this implies that gamma 1 is equals to integral from 0 to infinity exponential minus t dot 1 dt. So hence, gamma 1 is equals to, integrating this, we have exponential minus t over minus 1 running from 0 to infinity. Okay? Now, to differentiate exponential, to integrate exponential, you differentiate the numerator, differentiate the power, and the power is minus t. Differentiate, you have minus 1, you divide by the exponential function. That is how to differentiate, to integrate exponential. Now from here, we now have that gamma 1 is equals to, substitute the highest value, we have exponential, this time this will still give us infinity over minus 1 minus, in the bracket of substitute the lower part, we have exponential, this time 0 is still 0, okay, over minus 1. Now from here, this place will become 0, okay, anytime you raised a number to infinity, it becomes 0. So we have that gamma 1 is equals to minus times minus will give us plus exponential 0, which is equals to 1. Therefore, gamma 1 is equals to 1, as we have proved it. So you observe that gamma 1 is equals to 1 from our proof. Look at it very well. Now from here, we go to the second property. Now, second property says that gamma x plus 1 is equals to x gamma x. So we are to prove that this is true. Now to prove that this is true, we still make use of our definition, solution. We are still going to make use of our definition. What's our definition? Our definition says that gamma x plus 1 is equals to integral from 0 to infinity exponential minus t raised to x minus 1 plus 1 dt. Here, x is x was added, 1 was added to x. So here in this definition, we are going to add 1. That is why we have it. So from here, gamma x plus 1 is equals to integral from 0 to infinity exponential minus t raised to x dt. Okay, this will cancel this. So that is what we have. Now here we apply integration by parts. We apply integration by parts. How do we achieve that? We know that gamma x plus 1 is equals to, this is acting as u. So keep u times v, which is exponential minus t over minus 1 minus, differentiate this, we have x integral from 0 to infinity of v du exponential minus t over minus 1 du times x minus 1 dt. Okay? Now from here, what we have is this, that we have t raised to x exponential minus t over minus 1 running from 0 to infinity minus times minus is plus, x integral from 0 to infinity exponential minus t raised to x minus 1 dt. Now remember, this part, all of them will go to 0. Okay, so we are left with this part only. And from here, what does this place define? This place define gamma x. Define gamma x. Okay, so therefore gamma x plus 1 is equals to x gamma x. Proved. Okay, now number 3, let us look at the third property. Let us look at the third property. So number 3, we are going to prove that gamma x plus 1 is equals to x factorial. We are going to prove that gamma x plus 1 is equals to x factorial. Okay, now starting from here, from this place, we know that solution, we just have to start again. We know that gamma x plus 1 is equals to integral from 0 to infinity exponential minus t raised to x dt, right? So integrating this by part or using a reduction formula, so we have that gamma x plus 1 is equals to t raised to x exponential minus t minus 1 running from 0 to infinity plus x integral from 0 to infinity exponential minus t raised to x minus 1 dt. I believe you know this. It's gotten from here. What we did when this multiply this, we give us this minus. So this is where I am. So from here, this part will go to 0. So the part I have is gamma x plus 1 is equals to x integral from 0 to infinity exponential minus t raised to x minus 1 dt. So we are going to integrate again. Okay, this is the first integral. We are going to integrate this again, where this is our v, our dv, and this is our u. Okay, so we have that gamma x plus 1 is equals to, keep this x open bracket. Now this is our u, t raised to x minus 1. This is our dv, all over minus 1, running from 0 to infinity, minus, then differentiate this. We have x minus 1 integral from 0 to infinity exponential minus t all over minus, that minus will turn this one to plus, dot t raised to x minus 2 dt. Okay, so from here we have that gamma x plus 1 is equals to x. This part will go to 0, remember. So x times this is x bracket x minus 1 integral from 0 to infinity exponential minus t raised to x minus 2 dt. So continuing this way, that is, if we integrate this again, we'll be having gamma x plus 1 is equals to x minus 1 x minus 2 dot dot 3 2 1 gamma 1. So therefore we have that gamma x plus 1 is equals to, a number that moves like this is called factorial. So we have proved that gamma x plus 1 is equals to x factorial.